Okay. So, we are talking about the normal shocks, and we just started deriving the normal shock relation, and what we obtained finally in the last lecture is that the Prandtl relation, which is which provides the relationship between a star and the velocities between upstream and the downstream. So, this Prandtl relations that we obtained, this is what we can see the proof of it. So, that is now let us say what we have is that from here what we have is that gamma plus 1 by 2 gamma u 1 u 2 u 2 minus u 1 a star square plus gamma minus 2 gamma u 2 minus u 1, which is u 2 minus u 1. So, now we divide u 2 minus u 1, and what we get is that gamma plus 1 by 2 gamma u 1 u 2 a star square plus gamma minus 1 by 2 gamma equals to 1. So, even doing bit of little bit more maths, what we get gamma plus 1 by u 1 u 2 a star square 2 gamma minus gamma plus 1, which is gamma plus 1. So, once that cancels, we get a star 1 is u 1 u 2. So, this is what you get. Now, if you solve for the A star, then that can gives us like A stars equals to u 1 u 2. So, what we can do u 1 by A star u 2 by A star, which is 1, and that provides our m 1 star into m 2 star is 1, which means m 2 star is 1 by m 1 star. So, if the flow ahead of shock is supersonic, that means m 1 greater than 1, which means m 1 star greater than 1, then from this m 2 and m 1 star relationship, from this one we can say thus we will have shock behind the flow field behind the shock, where m star would be less than 1. So, if m star is less than 1, that means the m 2 would be less than 1. So, which proves that hence m behind shock wave is always subsonic. Okay. So, this is behind normal shock, because this relationship is for normal shock relationship. Now, further one can extend this what we got from, let us say, equation 13, what we do or can write m 2 m square equals to 2 by gamma plus 1 by m star square minus gamma minus 1 So, from here what we get, m star square equals to gamma plus 1 2 plus gamma minus 1 m square. Okay. So, we can again see this is equation 20. So, what we have is m2 star equals to 1 by m1 star. Now, we put equation 20 here, what we get, gamma plus 1 m2 square by 2 plus gamma minus 1 m2 square equals to gamma plus 1 m1 square 2 plus gamma minus 1 minus 1. Now, if we solve for m2, that yields m2 square is 1 plus gamma minus 1 by 2, which is m1 square minus gamma minus 1 by 2. So, this is what we get. So, let us say if m1 is 1, that means it is sonic, then m2 would be 1. So, this is something you can say this is infinitely weak normal shock, which is sort of defined as Mach wave. If m1 greater than 1, then the normal shock becomes stronger and m2 becomes less than 1. However, m1 if it tends to infinity, m2 tends to some finite minimum value, which is gamma minus 1 by 2 gamma. So, that comes around 0.378 for year. So, these are the different relationship that one can obtain. Now, again from equation 14 we get rho 2 by rho 1 is u1 by u2, which is u1 square by u1 u2, which gives us u1 square a star square, that would be m star square. So, that provides the relationship like rho 2 by rho 1 is u1 by u2 is gamma plus 1 m1 square 2 plus gamma minus 1 m1 square. So, we get an that relationship between the density across the normal shock. So, same thing one can obtain for the pressure, let us say P2 minus P1, which is rho 1 u 1 by 2, which one can write rho 1 u 1 square 1 by u 2 by u 1. So, a 1 square is gamma p 1 by rho 1. So, that is allow to write 1 minus u 2 by u 1. Now, since this has a ratio of the velocity from equation 21, if we use value of u 1 by u 2, we get p 2 minus p 1 by p 1 gamma m 1 square 1 minus 2 plus gamma minus 1 m 1 square gamma plus 1 m 1 square. So, p 2 by p 1 is 1 plus 2 gamma gamma plus 1 m 1 square minus 1. Okay. So, that is the relationship between the pressure ratio across the normal shock, and the other way the T 2 by T 1 is P 2 by P 1 into rho 1 by rho 2 H 1 by H 2 1 plus 2 gamma 1 into gamma plus 1 m 1 square. So, when m tends to infinity, m 2 would be gamma minus 1 by 2 gamma, which is 0.378, or P 2 by P 1 would be gamma plus 1 by gamma minus 1, which is 6. Rho 2 by rho 1 would be infinity, T 2 by T 1 is also infinity. So, now using the second law of thermodynamics, what we can write using second law of thermodynamics, what we can write H 2 minus H 1 C P ln T 2 by T 1 minus R ln P 2 by P 1. So, this is what we have already derived. Now, the H 2 minus H 1 is greater than 0. Now, so what we can do, let us say if T 2 equals to T 1 and P 2 equals to P 1, then this becomes 0, but for m equals to 1, H 2 minus H 1 equals to 0, but for m 1 greater than 1, H 2 minus H 1 greater than 0, m 1 less than 1 also H 2 minus H 1 less than 0. So, this is an impossible situation. Why? Now, another situations, since m1 greater than equals to 1, which means m2 has to be less than equals to 1. So, rho 2 by rho 1 greater than equals to 1, P2 by P1 greater than equals to 1, T2 by T1 greater than equals to 1, U1 by U2 greater than equals to 1. So, U2 by U1 less than equals to 1. So, which clearly means pressure, density and temperature, they increases across the shock wave, and velocity actually and Mach number decreases across the shock wave. Okay. So, that is what happens when you have a normal shock. Now, we look at the change in stagnation properties. So, we have a normal shock here. So, let us say we have a fluid particle like this. So, that has been m1 greater than 1. So, m1 and p1 and t1 and s1. This is an imaginary place, it is a state 1a, where the fluid element has been brought to rest isentropically. Now, m2 less than 1, here with the fluid particles. So, this is m2, p2, t2, s2, stagnation for 2 to 2a, which is p naught 2. So, this would be p naught 1, t naught 1, s1, p naught 2, t naught 2, s2. Now, from energy equation, what we can write, that is equation 4. Using equation 4, we write Cpt1 plus u1 square by 2 is Cpt2 plus u2 square by 2. For 1 goes to 1a, that means the fluid particle from here, this was brought to rest, which is a sort of an imaginary point. Isentropically, the then this should be Cp T1 equals to Cp T naught 1. Similarly, for 2 to 2a, Cp T2 is Cp T naught 2. Okay. Now, Cp T naught 1 is Cp T naught 2. So, that means what we get, the stagnation temperature remains constant across a stationary normal shock wave in a calorically perfect gas, which is CPC. That means, now this is very important that we say it is a stationary normal shock wave, because if the normal shock wave is moving, then this condition may not be valid. So, when the shock wave is stationary and it is a normal shock wave, then the stagnation temperature across the normal shock wave remains constant. In general, the stagnation enthalpy is constant. Enthalpy is constant across a stationary normal shock. Okay. Now, for chemically reacting gases, if there is a chemical reaction, then T naught 1 would not be T naught 2, since Cp is not constant anymore. Now, consider the changes between the imaginary state. So, considering the changes between the imaginary states 1a and 2a, S2a minus S1a, which is ln minus R by P1a, and what we have S2a is S2, S1a is S1, T2a is T1a equals to T naught, and P2a is P naught 2, P1a is P naught 1. So, what we get S2 minus S1 minus R ln P2 by P naught 1. So, what we could write P naught 2 by P naught 1 is S2 minus S1 by R. So, that is what you get for stagnation pressure ratio relationship. Since S2 minus S1 greater than 0, P naught 2 by P naught 1 would be less than 1, which clearly means then the total pressure or stagnation pressure decreases across a normal shock. Now, we can get the density too. Rho naught is P naught by R T naught. So, what we can write, rho naught 2 by rho naught 1, P naught 2 by P naught 2 by T naught 2 into T naught 1 by P naught 2, P naught 1, which is, since the stagnation temperature is same, this will become P naught 2 by P naught 1, which is also less than 1. That means the stagnation density is also so is rho naught 1. That means across normal shock, stagnation pressure and density decreases, whereas stagnation temperature remains constant. Okay. So, what we had is that fluid particles from here. So, this has gone to state 2A and this has gone to 1A. So, this is 1, this is 2. For adiabatic 1D flow, we can again write Cp T1 plus U1 square by 2 is Cp T2 plus U2 square by 2, which will get us Cp T1 plus Cp T01 and Cp T2 plus Cp T02. In Cp T01 equals to Cp T02, T01 equals to T02, since Cp is constant. And again we can write the change in entropy, which is delta S, let us say S2 minus S1 Cp ln T2 by T1 or P2 by P1. So, the delta S is 0, which is Cp T ln T2 by T2 equals to R ln P02 by P01. So, we convert things in the terms of stagnation condition. So, what we get ln P02 by P01 would be 0, which means P02 by P01 is 1, that is P02 is P01. So, from perfect gas law, what it gets, P0 equals to rho r T0. So, that means rho naught is P0 r T0, which is constant. So, this brings to a very important conclusion that for isentropic flow, P0, T0, rho naught are constant everywhere in the flow. So, which means whenever you have an isentropic flow, your stagnation properties remains constant everywhere, but whenever you have stationary normal shock, just again I am reiterating that it is a stationary normal shock, then your stagnation density, stagnation pressure that decreases, but stagnation temperature only remains constant, and across a normal shock density increases, I mean static density increases, static pressure increases, static temperature increases, whereas the flow velocity decreases in the downstream of the shock. So, that is pretty much what we wanted to talk about in normal shock relations. So, what we will do, we will just talk about the oblique shock and other stuff in the next lecture. We will stop about this here today.